So welcome back. And the topic this week is to go through some of the gritty, nitty details of how we implement the Boltzmann machine with a given ansatz for the trial wave function. And last week we went through some of the basics of so-called energy-based models, of which Boltzmann machines are one of the typical applications of a machine learning, a certain branch of machine learning, which is called generative learning. And the possibilities which we have for the second project is that we extend project one and change the trial wave function with a Boltzmann distribution. And this Boltzmann distribution is going to have a specific model dependency, because we're going to assume that it has a specific form. And we are going to look at what's called a Gaussian binary model. And I'm going to explain briefly what that means. We have binary-binary. We can have binary Gaussian, Gaussian-Gaussian. You can make it more complicated. And the basic philosophy is that you have a probability model where you have some function f. And the function f here is going to be replaced by an exponential with the energy as an argument. And z is the partition function, or just a normalization factor, if you're thinking of that in terms of a probability distribution function. So what we did last time was to discuss these marginal and conditional probabilities, which at the end, because our probability function will depend on the visible layer, which then can represent the degrees of freedom of the system. It could be the coordinates and the positions of the particles. So if you have two particles in 2 dimensions, you would need 4 degrees of freedom. And this H is what is called a hidden layer and represents the parameters of a neural network. And you can make this in different ways. You can have a neural network. You can use a Boltzmann machine or a restricted Boltzmann machine, which is a system which is much, much simpler. And for some of these marginal and conditional probabilities, so this is the marginal one because you sum away one of the degrees of freedom. And then because we are interested in just P of X. And when we do that, if you just scroll down here, the typical approach you end up with is to optimize this probability distribution as a function of these parameters theta. For those of you who take machine learning, you've probably seen this before. The philosophy is basically the same. And when you then maximize this, you would maximize the log, because that's easier than maximizing the product of the individual probability, where we have assumed that all the stochastic events are independent and identically distributed. And this leads to, in statistics, what's normally called the maximum likelihood estimator, when we have optimized with respect to this parameter theta and find the best possible or the optimal theta, or estimator, as it's also called. So if you go into a textbook in statistics, you will find this equation, which you see here, as something which is called the maximum likelihood estimator, where we then find the optimal theta by maximizing this. And since a product is not so nice to evaluate in terms of gradients, you take the log, which is an equivalent problem. If you take minus log, then you have a minimization problem, because then it's a convex function. If you take the maximization approach, then you have a concave function, and the log is either concave or convex. So that's a very nice function to optimize. And this is a basic recipe in statistics, and you end up with this problem here. Now, in order to set up, if you want to set up your own Boltzmann machine, you would then need to calculate these different, so if we just scroll down a little bit, you would then need to calculate the different marginal and conditional probabilities, because the different nodes will fire with a given probabilities. Now, when we are setting up our Boltzmann machine, we can actually get away with a simpler approach. And this is what we are going to go through today, because what we are optimizing is not the probability, but we are optimizing the energy. So we will use this probability, which you see here, as our wave function. And you can choose to have this as a wave function squared, or you can allow this to be the square of the wave function. So it's up to you, but it's normally normal to actually take this as the wave function squared because it's a probability. The only thing when you use a log is that when you take the log of this function is that if you take the square root or not, you will just get a factor of 1/2, 1/2. So that's just a simple factor which comes in addition. And the typical Boltzmann machines are then given by some functions which you can choose. So if you choose a binary case where x and h can just take binary values like 0 and 1, then you would have a function here which depends on this a, which is a parameter which you can call for the bias. Same with b. And then you have the weights which link the hidden layer with the visible layer. And this is a pretty standard approach which people used in Boltzmann. So Boltzmann machines were actually very popular till convolutional neural networks and neural networks really kicked in 2010 and on. So people try to use Boltzmann machines for image recognition and classification. And then when people developed convolutional neural networks and got better and better reproduction of data, then the Boltzmann machine as a competitor to CNNs was basically just gone. But in 2017, Carleo and Troyer revived the Boltzmann machines in the applications to quantum mechanical systems. But as you will see, this kind of model here may or may not include important properties of the wave function. And if you look at this one, if you now look at the way the probability is, if you think of this as a wave function squared, then you see that if you have a harmonic oscillator, you don't have an x squared dependence. So clearly this will fail pretty miserably if you apply this to a harmonic oscillator type of problem or any type of problem where the quantum mechanical wave function goes like either e to the minus r squared or e to the minus r. So you would actually miss that one. So many people use this as a trial wave function, but multiplied with some physics. Now, what we are going to do now is in the examples here, we're going to look at a Gaussian binary. So this value a and x is now going to be given by x squared instead of a linear dependence. And then it will be a harmonic oscillator lookalike. What we will be missing would, however, be the correlations between particles. And what you could do then is to take this trial wave function or probability and multiply it with a Jastrow factor, as we did in project number 1. And then you can bake in more physics. This part here, if you're dealing with fermions, will not include the anti-symmetry property. So what people would do then would typically be to multiply this one with a Slater determinant or determinant, which then brings in a simple way to include the anti-symmetry for systems of fermions. So you could think of this as a way to simply bring in additional parameters to perform the optimization. So this is roughly where we will stay. For those of you who follow the course on machine learning, advanced machine learning, then you can combine the report here with that course, but then you would replace this probability distribution with a neural network. And that does actually a much, much better job. But still, for a neural network, you need to guide the network with symmetry considerations. So like a neural network would struggle a lot to recover the anti-symmetry of a fermionic system. So that means that you often end up with taking a neural network and impose it to be symmetric, and you would multiply that one with a predefined Slater determinant. And then you bake in automatically the anti-symmetry, just making sure that this function here then would be symmetric. Because if the total function has to be anti-symmetric, then you need to guarantee that the total wave function, if one part is anti-symmetric, then the other one has to be symmetric. So what I wanted to do now is actually, if we look at the Boltzmann machines here, in the lectures which we had last week, we actually looked at the way you can derive all these different, probabilities. based on the type of binary or Gaussian binary model which one chooses. So the probability then for a binary is given by this expression here. And then you can find the marginal probability where you would sum over all the hidden nodes. So you would need that in order to find out how a node in the visible layer and how a node in the hidden layer fires. So you can see now these derivations here. You would also need this one. And you would also need the conditional probability. What is the probability of H given X? We don't need to look at that when we deal with the quantum mechanical approach here. So I just wanted to go down here now and go through the basic equations, because this is put in here for completeness in case you would like to write a general Boltzmann machine where what you optimize is the probability. But what we are going to optimize in a neural quantum state is a wave function where we are going to assume, if you now look at this one, we are going to assume that this is given by the Boltzmann machine, where this F is now the restricted Boltzmann machine. So this is going to be the trial wave function. And if we have that, we can then find the expressions for the different derivatives which we need to code. And this is what I wanted to go through on the whiteboard here. So let's just switch to the whiteboard and go through these final details, which we then need to code. And at the end of the Jupyter notebook, what you will find is actually a code which implements the non-interacting case. So we are going now to assume for a Boltzmann machine. So let's just set up the date here so we have that correctly. So we are going to look at the so-called restricted Boltzmann machine. And I'm going to use this acronym BM. And this is normally written as an RBM here. And in our case, what we have would be a hidden layer with a given number of hidden nodes. And these become a parameter in the theory. So we could have a set of hidden nodes here. And then we have, let's call this H1, H2, and all the way up to Hn. So these are the number of hidden nodes. And then we would also have a number of visible nodes. So these are the visible or just the input layer, visible layer. It's often also called just the input layer. Now you can stack these hidden layers and make the network deeper and deeper. But then from experience, the model has become much more difficult to train. So we would have an X0, now X1, we just correct that one. X2, X3, and this goes all the way up to Xn. And then these different layers are connected. So there will be a connection between X1 with H1, with H2, etc. And the same with X2 here, and all the way up here, etc., etc. I'm just writing this in a generic way here. There is no connection between the nodes in a given layer. Originally, when people proposed the Boltzmann machines, there were also connections between the nodes in a given layer. And that makes the training even more difficult. So what we are going to look at is now an ansatz where we will assume that a trial wave function. So we can now assume that psi, and I'm just going to write this in a generic way with psi of x here. And this will be, now let me just write this a little bit better. So we are going to have a trial wave function where x now can be a vector which contains the positions of all the particles. And this is going to be given by 1 over z of theta. This is the partition function, which depends on the parameters. And then we have e to the minus e, and this will contain x and theta. Now we have summed over so this is actually a sum over, so z is a normalization constant, but we are actually summing over all the possible hidden layers or hidden nodes. So I'm just going to write it like this. And this function will then be a function of E of X. And then I have the hidden nodes. And then I have the parameters theta. So as I said, we can have a binary. We can have a Gaussian binary. So a standard choice for quantum mechanical studies of a harmonic oscillator type would be something like a Gaussian binary. And then we will put this energy function of X, of H, of theta. And I'm just going to write it out here. It's going to be a function of I equal 1 up to m. And then we have xi minus ai squared. Now, the x's can now be the positions of the particles. So if we have two particles in two dimensions, as you will see from the example in the notes, then we are going to have 4 visible nodes. And then you can play around with the number of hidden nodes. That becomes a parameter. So you can increase it or decrease it, etc., etc. Now, this comes often with something like number 2 here. You will see that when we take derivatives, and a variance. But normally we put that variance to 1 because we don't know that. So we put that one sigma squared to 1. Now, we're also assuming that the wave function here for the ground state is a real valued function. That is an approximation we will make in project number 2. In general, the trial wave function is not only real, it's a complex object. So the Gaussian binary is going to look like this, and then we will have a sum over the hidden nodes, j equal 1 up to n. There's going to be a parameter b, which is the same as the bias in a normal neural network of hj. And finally, we have a sum over the correlations between the hidden layers and the visible nodes. Like that. So this is a model for the wave function. And when we plug that in, we can then calculate the probability distribution, so in a pretty efficient way. So I'm just going to show you, before we do that, I'm going to set up the expression for z. So that will be a sum over all the possible values of x and all the possible values of h. So these are all the configurations which we have. And then we have e to the minus beta or minus e of x, of h, and then theta. And the parameters theta, they are given by, so this is a collective container for A, which you can interpret as a bias, same as B, and then the matrix W, which contains all the weights. So that is just the preliminary step. Now, what it means, if we now look at this partition function where we sum out all the hidden layers, because now the hidden variables, h of j, they take values of 0 and 1, whereas x takes values between minus infinity and plus infinity. So we're assuming that x is a continuous variable, and that's why we use a Gaussian binary. Now you can, suppose now you were to look at the hydrogen atom, where the wave function goes like e to the minus r, then you could have an exponential distribution, which you would then use instead of a Gaussian. And then you could have an exponential binary. You could combine the hidden layers with a Gaussian distribution. The only thing then is that everything you do would become more and more complicated. So the thing which I'm going to bring in now as an additional element, which we are going to need, is the calculation of the marginal probability, because that's the one we are interested in. So we want a trial wave function. If you look at this one, which now depends only on x and theta, and we are going to optimize our energy with respect to that quantity. So that means that we need to perform this summation by inserting this specific formula. Now, since the h values run over 0 and 1 only, so it's a binary case, we can actually set up this function and find that the trial wave function which we have, or the probability, which is the same of x of theta, when I do the summation, then you see that if you go back to this expression here and I plug in this term, this is independent of h. This term here will depend on whether h is 0 or 1. And this term here will also depend on whether h is 0 and 1. So in case h is 0 in this summation here, then, so this is actually a sum. This is a more, how to say, actually a sum where I have h1 equal 0, 1. I have a sum over h2 equals 0 and 1. And it goes up all the way up to the final h of n equal 0 and 1. So if I do this summation, then I will get, if case h is equal to 0, then I will have a term here, which will simply give me 0 here. And since we have an exponential, I will then have 1. E to 0 is 1. I will also get a 0 here, and that will give me just 1. And then I will have a term where h is equal to 1. And that means that I will have in the exponential an argument bj and xi wij. So that means that I can rewrite the sum which you see here, this one, by setting in the values for h, all the h's. So I will get 1 over z of theta, and then I'm going to have e to the minus, and then I will have a sum over I equal 1, and I'm going to put this variance equal to 1. So I have ai squared divided by 2, because that is not affected by the sum over the h's, or the hidden layers. And then this has to be multiplied with a product over all the hidden ones, because the hidden ones take values 0 and 1 only. And I get 1 when h is equal to 0, plus e, and then I have a b of j, plus, and then I'm going to have a I equal to 1 of m of xi of wij here. And this comes with a minus sign. Okay. So that's going to be the expression for the trial wave function squared. Some people have tried different ansatses where they square this one and then use that one as a trial wave function. And this is actually what you end up with. And that will only give us an additional factor of a half, because when you take the square root and then the log, because what we are going to do is actually to take the log of this quantity. So the trial wave function is going to be the square root of this quantity. We are assuming that the ground state has a real function. So if we have a complex function, we need to be a little bit more careful. So everything here assumed to be real parameters in the approximations we are going to make. And the trial wave function will then be the square root of this quantity, and that's what we will plug in when we take the log of that quantity. So let me now remind you of some of the quantities which we need. So this is the trial wave function, the way we are going to plug it in terms of a hidden layer and a visible layer. So instead of us having the standard harmonic oscillator, we have an additional term here, which now become the parameters of a neural network, which then are trained repeatedly. Okay, so the next thing we need is now to go back and look at the local energy, which we defined as 1 over psi of h times psi. And I'm not going to use a subscript t here. Psi is now the trial wave function. And that trial wave function, in our case, so psi of x of theta is going to be given by the square root of this Boltzmann distribution, or p of x of theta. Now, one of the things we know then is that what we need in the optimization is to take the gradient of the expectation energy of the local energy. And this is exactly what we did in project number 1. And now instead of, if you think back about what we did in the beginning of the lectures and also the previous week, then when we optimized a standard Boltzmann machine, we were optimizing the probability. In the quantum mechanical case, we are not optimizing the probability, but we're optimizing the expectation value of the energy. And now, instead of having just some 1 or 2 parameters as we had in project 1, the parameters are going to be the variables of a neural network. And that means that what we need, if we just bring back what we had in project 1, is the expectation value of the local energy multiplied with 1 over psi, and then we have the derivatives. And I'm just going to write this as a d psi of d theta. So we have the different parameters. This is one expectation value, and then we had the next expectation value, which was EL, and then we have 1 over psi of d psi of d theta. And this is the expectation value of the gradient. And we are just going to reuse the same equations which we had for the optimization and same method as we had in project 1, except that now we have to calculate derivatives of the trial wave function with respect to new parameters. So the thing which can make things a little bit easier is to rewrite this one in terms of d of ln of psi of d theta. So this makes life a little bit easier because what we have then is a set of parameters which now are going to be given by the different variables theta. So the partition function is a constant, so we don't need to think of that one in the optimization here. And the nice thing with the log here is simply that we have an expression which is given by this quantity here. So that means that when we take the log of that one, we simply have to take the derivative of this one. So if we then look at the log of the trial wave function, so the ln of psi is then going to have a term which goes like ln of z. This is a constant, so we can often discard it. And then I have minus, and then I get a minus here, and then I equal 1 up to m, and then I have my x of I minus ai squared, and then I divide this by 2, and then I have plus a term here, which goes like the sum over all the j equal 1 up to n. It's actually a minus sign here because we have a minus sign. So let me just do it properly here. Minus, and then I have ln of 1 plus e and minus, and then I have a bj plus a sum over I equal 1 up to m, and then I have xi wij. And then what we need are then the following equations. So we need d ln of psi of with respect to ai, these parameters. And you see that that one, if I take the derivative of that, since I have a minus there, I get a my plus. So this gives me simply 1, actually, since I get rid of xi minus ai. So that's pretty easy to implement. Then the next term I need to look at is a d ln of psi of dia. No, sorry, db. And that's going to be given, so I have a minus sign there, and that's going to be given by 1 divided by 1 plus e of minus bj plus I equal 1 up to m xi wij. So when we have this log exponential ansatz for the wave function, life becomes much, much easier. Because then what we have is simply to take the derivatives of a ln of psi with respect to the different parameters. Then the final equation which we need is actually this d of ln of psi of d wij, and that gives us a minus, and then I have an x of I of 1 plus e, and then it's the same function which we have seen before. Sum of I equal 1 up to m xi and wij here. Okay. So this is something which is pretty straightforward to implement as soon as we have the different parameters, and then we can calculate the respective derivatives, which we need in the gradient optimization. So when we calculate these quantities, what we need to plug in then is an expression for this one and for that one in the calculations of those integrals. So in the slides, in the Jupyter Notebook, you will actually find an example of code which implements exactly these expressions. So then the next thing we need is to rewrite the local energy. And then we're basically done, because then we have the derivatives. We have an ansatz for the trial wave function. Instead of harmonic oscillator, we have a Gaussian binary Boltzmann machine. We have the derivatives with respect to the parameters we want to optimize. And then we need simply a new expression for the local energy. And in our case, when we look at the local energy, we know that we have decided that this is going to look like 1 over psi. And then we have h, the Hamiltonian, acting on psi. In our case, the Hamiltonian is going to look like as follows. It's going to have a sum over p equal 1. And since I've been using n and m now for these hidden and visible nodes, I'm going to write an upper p here for the number of particles. So this p here is number of particles. Just to distinguish it from n and m, which are reserved for hidden layers and for the visible layer. And then we are going to have a kinetic energy term, minus 1/2. And then I have a second derivative. And then I have the harmonic oscillator, plus, and it's going to have a harmonic oscillator frequency. It's going to be the position of the particles like this. And then we are going to have a potential P, that's double sum. And I'm just writing this in a generic way, which is a function of the relative distance. So this RPQ is simply going to be the relative distance between two vectors. And I'm using natural units. So that means that I'm putting H equals C, equal the charge, equal the mass of the particles, and I put everything equal. So if I plug this in, you see now that we are going to assume that this one does not change the act when it's acting on the wave function. It does not change the wave function. Same with this one. It doesn't change the wave function. So the only problematic term is actually this one. So if I look at the local energy then, this is going to look like as follows. I will get an E over L, which is going to be given by minus 1/2. And then I have 1 over psi. And then I will have the sum over P equal 1 up to the number of particles. And then I have my del P. And this quantity here is then multiplied with psi. And then I'm simply getting the potential energy from the harmonic oscillator, P equal 1 up to the number of particles. And this is just going to be given by this term here, where we simply loop over the particles, as we did in project 1. And then we are going to have a final term where we also have assumed that the two-body interaction does not change the form of the wave function. Now there is a nice trick which we can use. And if we just do this in one dimension, so let's say that we have one particle in one dimension, in one dim. That means that this term which we have, del p of psi, is simply going over to d of dx times psi. And psi depends just on a variable x then. Now we can actually now reuse this logarithmic approach, because we can actually rewrite this term which you see here, this one. So this term is something which we can rewrite as, so let's just go through that. So I can actually rewrite this term. So what I'm having is 1 over psi, and then d of dx of psi. And you can, it's actually not so difficult to show that, but you can show that this one becomes equal to d of dx of ln of psi squared plus of d of dx squared of ln of psi. So you can just try it, and you will see that that's going to give you the same expression as you have on the left-hand side. Now, this is beneficial for us, even if we now introduce more derivatives, because we can easily now set in these expressions in the calculations, because then we have that ln of psi is something which we have already calculated, and it's something which then is pretty straightforward to plug in. So we have ln of psi is now simply going to be given by these terms here. And that means that when we now go back here, we will simply just take the shape of the function and plug that one in here. And since you have derivatives with respect to x only, and if you look at the partition function, this term here, this depends only, it does not depend on x and h. So that means that the derivative of this quantity here with respect to x and h is equal to 0. So it means that the only thing we need to take into account here are those terms which we have in the Gaussian binary ansatz. And then we have an exponential, so that take a log of an exponential, and that means that the only things we need to do now is simply to set in, so we have ln of psi, which then simply becomes, and we leave out the partition function, so that will simply have now xi minus ai squared divided by 2 here, and then we have the next term, which is minus, and then we have this, if we now go back here, what we end up with is a term which goes like ln of this term here. So minus, let me just set it up here so that we have everything for the sake of completeness, because then we end up with minus, and then we have a sum over j equal 1 up to n, and then we have ln 1 plus e of minus, and then bj plus, and then we have a sum over I equal 1 up to m of xi wij. And then we take the derivative with respect to x of these quantities. And calculating the derivatives with respect to x is actually pretty straightforward. So the first one, d ln x, which we're going to take, will then simply give us, if we look at this term here, that will give us simply a factor of 2 times x divided by 2. So that is just x. And then I have xi minus ai. So that's pretty straightforward. And then I need to take the derivative with respect to that one. And that will simply give me a wij. And then I will have a denominator which contains ln of this, or 1 plus this term here. So this is pretty straightforward to implement. And these are actually the expressions which we need in project number 2 now, compared with project number 1. So after the break, I thought we could look at the code. And then we have essentially all the ingredients which are needed if we are looking at two particles only. And then I was also thinking that we could say a little bit about possible extensions to more than just two particles. And then we can then, if we do more than two particles, we can think of looking at project one and then simply look at the system of bosons. Or alternatively, we could now look at a system of fermions with more than two fermions, because the kind of harmonic oscillator systems we can look at in terms of two electrons in, let's say, in two dimensions, moving in a harmonic oscillator trap, which is a so-called quantum dot system. If we move beyond two electrons, we need to be a little bit careful with us implementing the anti-symmetry of the wave function. Okay, should we take a small break? So let us try to wrap up the session today by looking at the final codes. So the kind of expressions, and we will normally just put this sigma, which is plays the role of a variance. We just put it to 1. So you could think of this as being a normal distribution you're using, a Gaussian, with a given mean value, but with a variance which is set to 1. Because often we don't know that one. You can think it of as a parameter we can tune, but in our calculations, we're just going to put it to 1. So these are the derivatives which we would need to plug in. And then we also have this log of the trial wave function, which is then going to be given by the expression which you see here. And this is also a quantity which we will need when we calculate the local energy. So the code example here is a code example where I have implemented the Gaussian binary for a system of two electrons in two dimensions. And these electrons are confined to move in a harmonic oscillator trap. So it looks very much like what we have from project number 1, except that now we are going to look at two fermions. Now, let me just go back to the whiteboard a little bit, because I wanted to say a little bit about the physical system. So before we look at the code, let's now take a quick look at the physical system. So the physical system, I mean, we can, if you guys would like to, this is also another option, is to replace the fermionic case with the bosons. And then you would simply plug in the kind of function which you had before for the Jastrow factor, and you would multiply that with a neural network or the Boltzmann machine. But the system which we have here is a system of two electrons. Two electrons in a two-dimensional, in a two-dim harmonic oscillator trap. Now, for simplicity, we are going to put H, we're using these natural units as they're called, and we put the mass of the particle, the electron, equal to 1. What we're also going to do now is to set the oscillator frequency. We just set that one to 1, but we can change that one. So there's no problem in changing the oscillator frequency here. So we put the oscillator frequency to 1. So that means that the ground state energy, so you could now think of this as a system of two electrons. And when we now look at the harmonic oscillator energies, which we have, we are going to have to be a little bit careful now. So in 2 dimensions, so this is in 1 dim. When we now move to 2 dimensions, so in 1 dimension, then we know that the energy is just a quantity which depends on the quantum number n. So this will be n equal 0, n equal 1, n equal 2, etc. So this is given by h bar omega of n plus 1/2. That's in 1 dimension. But we are going to move into 2 dimensions, and then we need to be a little bit careful here. So when we go to 2 dimensions, then something happens, which we need to look at. So in 2 dimensions, so let me put up the harmonic oscillator well here. But now we have an energy which will depend on nx and ny. And in this particular case, we have h bar omega, and we have nx plus ny plus 1. That's the single particle energy. Now, when we have a system of fermions, then we need to be a little bit careful because the total wave function for fermions has to be antisymmetric. That's the Pauli principle. A consequence of the Pauli principle, when we write the trial wave function in terms of single particle states, is that you cannot have more than one fermion in a single particle state. So this last statement is not the Pauli principle, it's the consequence of the Pauli principle, which says that the total wave function has to be antisymmetric. So what you would have then would be a situation here where you now have nx equal to ny equal to 0. So if I have 2 electrons only, what happens then is that you could think of having 1 electron with spin up and 1 electron with spin down. That would be the trial wave function which you could set up as an ansatz. And you know that the wave function now for y of x and y, this will be a function which depends also on the quantum numbers nx and y. And this is x, y. And this will be given by a determinant. When we don't have an interaction, then without an interaction, this is the exact wave function. So we are just going to put a question mark here because I want to elaborate a little bit on with that one a little bit later. Now, if I have 2 electrons, this is the system which I have. When I now look at the next state, I can have the case with nx equal to 1 and ny equal to 0. I can have ny equal to 1 and nx equal to 0. That's the next energy level. Now, if I place the particles here and they're not interacting with each other, then the total energy, since nx and ny is equal to 0, the total energy has to be the energy of particle 1 plus particle 2. And that's going to give us just 2. So that's the kind of benchmark you will see in the code here. But you see that you can keep increasing this now because you can go to the next level and you can have nx equal to 2 and ny equal to 0. But then there's going to be a new state here where you can have nx equal to 1 and ny equal to 1. And then there's a new state, which is nx equal to 0 and ny equal to 2. Now, these systems are extremely popular systems in solid state physics, in condensed matter physics, in particular in semiconductor physics, because these systems are systems which are lookalikes of systems of electrons which are trapped in layers in semiconductors. So you can set up potential differences and trap single electrons. And these systems are called quantum dots. And they are fascinating systems because they exhibit magic numbers like you have in the periodic system or like you have in nuclear physics. Because now, if you follow the Pauli principle, it means that you would have to have, if you have 6 electrons, then they would fill up these states as well, would spin up and spin down. And you can see that the energy like, that if you try to break the energy, you require more energy than if you have 1 electron which is loose here. So the kind of the thing which you see in atomic physics with the ionization energy. So if you take the noble gas neon, you have 10 electrons, and you know that the separation energy for 1 electron that gives you the ionization energy is much larger for atomic neon, the noble gas, than it is for the next system, which would be sodium, where you have 1 electron in the free s orbit, and that electron is easy to knock out. So the ionization energy for sodium is much, much smaller than the ionization energy for neutral neon, which is a noble gas. And that's simply because in this kind of picture, you're filling up all these single particle states, and then it requires more energy to, let's say, break a pair and break one loose. But if you have a loose guy here, then you can radiate the system with that frequency and then knock it out. So these systems with the quantum dots, they actually exhibit magic numbers. And you can model them with harmonic oscillator potentials, because even if the potential is finite here, in the bottom, it looks like a harmonic oscillator. So the harmonic oscillator is a very good approximation. Now, if you don't want to do fermions, you can just take project number 1 and simply look at a bosonic system. And then you can add more and more particles here, because then you have spinless particles. Okay? So I hope you see the, so if you now look at the case with no interaction, that means only no interaction between the particles, then the exact wave function is actually given. So the exact ground state which I'm going to call psi 0, and then we are going to have R1 of R2 here, is actually going to be given by a Slater determinant, where I now have the wave functions. So there's going to be a spin part and a spatial part. So there will be a psi, and I'm going to call this psi 0, and I'm going to define what that is. And it has an R1, and then it's multiplied with a spin part. So, and the spin part is something which I will just label with a function like this. So there's a spin up part, and there is a psi still psi 0, because the electron is now assumed to move in the lowest lying state, but I have a spin down state. And then I have a psi 0 of R2. So the second column refers to the second particle. Oh, sorry, this got a little bit squeezed, so I just need to make it. So I have a psi 0 of R2, and this has a spin up part. And then I have a psi 0 of R2 times a spin down part. So this is a determinant, and that's going to look like as follows. I can now isolate the spin parts, psi R2. So this is now the spatial parts. And then I have a spin part, which is a spin up for particle 1. It's a spin down for particle 2 minus a spin down for particle 1 times a spin up for particle 2 here. So the second part is the spin part of the wave function, spin part. And this is the spatial part. So this the spin part is antisymmetric, so it means that the total spin is equal to 0. So when I fill up the single particle states, you see now I have the total spin, the projection on the z-axis is equal to 0. So there's only one spin realization. So the spatial part is symmetric, and the spin part is antisymmetric. This is pretty much like what you would see for the helium atom in 3 dimensions. So this psi, which you see here, this wave function, psi 0, is nothing but the spatial part for this state here. So that means that psi 0, if we now look at that one, psi 0 of Ri, a given particle, that is simply now the harmonic oscillator for nx. So this will be harmonic oscillator. This is a Hermite polynomial h of nx equals 0 of a function of x. The ny equals 0 for y. And this is x of I and y of I multiplied with e to the minus. And then we have this parameter alpha, which now incorporates the harmonic oscillator frequency times Ri squared multiplied with a normalization constant. So this constant is just a normalization constant, which is not so important for us. Now h of nx, or n of x, is a Hermite polynomial. And that Hermite polynomial, when I set n equal to 0 of x, that is simply equal to 1. So that means that this wave function which we have is actually proportional to e of minus alpha of Ri squared, where Ri squared is simply xi plus yi squared. And alpha is proportional to, so this is alpha, it's proportional to the frequency omega, the square root of the frequency, as we discussed in project number 1. So the trial wave function, if you now go back to what we discussed in terms of the Boltzmann machines, you see now that if I have this as a trial wave function, and I go back to the Boltzmann machine, which we discussed before the break, and look at the trial wave function which we put up, that trial wave function has a term which goes like xi squared. So we have a kind of basic property of the ansatz for the ground state for every single particle here. So that's why this single particle states, which we have for the harmonic oscillator, are going to give us, if we use a Gaussian binary, it's actually going to give us a decent result. But then it's not going to include a correlation part, that the Boltzmann machine, which means that when we now bake in the interaction, we will not get a very good result. And you will see that immediately when we run the code here. But you see, this is the basics. So that means also that the energy for this specific system, if I now look at the energy for nx equals 0 and ny equals 0, for one particle is going to simply be equal to h bar omega, which is equal to 1 when h bar is equal omega is equal to 1. So with two particles, then I will have E equal to, so I'm going to put this one. This is the non-interacting energy. Being E0. And this is exact for the non-interacting case. This is now going to be given by simply by 2 times h bar omega, which is going to be equal to 2. So in the code, which you will see we're going to run now, you should get, hopefully, 2. If I add the interaction, in our case, the interaction for 2 electrons here is going to be the repulsive Coulomb interaction. So that means that the V of Rij is simply going to be given with these units which we have chosen, where all the constants are put to 1. This is simply going to be given by Ri minus Rj. Now, this 2 electron case can be solved analytically, even with the interaction. So can be solved analytically. And what you should get then is that E, the true ground state of this system, has to be equal to 3 in this atomic. So these are normally called atomic units, AU, times atomic units. You will see that when I plug in the interaction in the code, I'm not going to get this. So after the break, we are going to look at, if we look at this system here, we are now going to, after the break, we are going to look at how we can set up a system of 6 fermions, 12 fermions, etc. Because now when we have only 2, the trial wave function simply simplifies because the spin part is not going to affect the energy, because the energy Hamiltonian which we have is going to contain this part, which does not affect the spin degrees of freedom. So spin is a conserved quantum number. The kinetic energy does not act on spin, and the harmonic oscillator does not act on spin. So that means that when we calculate the energy now, the only thing which is of interest for the energy calculation, since the Hamiltonian does not depend on the spin degrees of freedom, is this part here. So we can actually use what we did in project number 1, simply because the spin degrees of freedom are not in the Hamiltonian. So there is no spin orbit term, There is no spin-spin interaction, etc., which we would need to take care of. So this simplifies life a lot. And the kind of system we will extend upon when we meet after the break is actually a system where we're going to have 2 more electrons here, 2 electrons here. So we will have 6 as a kind of magic number. We can add, if we are getting ambitious, we can add more electrons, and you can see that every state here has a degeneracy of 2, because we can have spin up and spin down. So that means that I will get 2 plus 4, so that is 6 as a new magic number. Here, I will get 6 more particles, so I can have 12 as a new magic number. And people have actually showed this experimentally, that you get different separation energies from the closed shell systems, where every single particle state is filled, to a case where you have an open shell, where you can have only 1 particle here. So these quantum dot systems are normally called artificial atoms, because they do actually exhibit magic numbers. So in 2 dimensions, you have magic numbers like 2, you fill up this one, you get 6, you fill up this one, you get 12, then the next one is 20, then 30, 42, 56, etc. So these are magic numbers which people actually showed experimentally that day. So the calculations which you see in that code is, if you exclude the interaction, we should actually get 2 here. So let's go back to the code. So this was about the physics of the system we have implemented. If you don't like this system, you can still stay with the bosonic system. And that makes life a little bit easier, because then you can just fill in bosons after bosons in the lowest lying state. So let's take a closer look at the code. So the code here simply implements these equations which we discussed before the break, these different derivatives. It implements this ln, which you see here. We don't need the partition function, because we're going to take the derivative with respect to x. So that means that this is just a constant, so we don't need to think of that. So you will encounter now, this is the wave function, and you can see now that it depends on the positions of the particles and the parameters A, the bias, and the bias B, and the weights W. So this sigma is a parameter which I just put to 1, as you can see here. So I'm not using that. And then I have this factor Q here, which simply sets up the part of the trial wave function, which we need. I mean, that is essentially this part which you see here, this argument here, which then will depend on B, and will depend on X and on the weights. And you can see that that is being called in here, the positions, the bias, and the weights. So that sets up this ln term. And you can see now that it takes simply these terms and it squares them. So it has a term, this Q here comes down. If you scroll down a little bit, you will find, so where did I put the Q here? Yeah, I have this function qfac. Let me just go down here. There we have it. So this is simply setting up this term, which is the argument to this log function, b plus temp here. And you see that this b plus temp now simply has r, the position, times the weights. And the rest of the code here, I have the quantum force as before, but now I take the quantum force for that specific function, which I have, which is actually simpler than the one we did in project number 1. And you will find the derivative of the wave function ansatz. And what is encoded here is simply these expressions which you see here. And then before the break, we discussed also the local energy. And now the trial wave function contains this logarithmic term, and then it contains also the term which now includes the position minus this bias A squared. And that is the term which we have here. And that's it. So it's pretty straightforward to set up. And then we have the local energy, and I'm setting up the different terms. I have d ln psi, of particle 1 and 2, and then I calculate the local energies by simply taking the expression of the derivative of this quantity here. So you can actually plug in simply analytical expressions. If you want to make a more complicated Boltzmann machine, you can do that as well, but then it's more convenient to use automatic differentiation. And then the rest here is as before. So it contains the position old, position new. It has the quantum force old and new as we did before. It has the energy derivatives, the derivative with the quantities which enter the calculation of the gradient. And in this function here, what you will find then is exactly these calculations of derivatives, the gradients, and the energy as we calculated before. So these are the energy derivatives. It sets up the gradients. I'm setting up number of particles equal to dimension 2. And what I'm doing now is simply to say that the number of hidden nodes is just given by 2. So this becomes a parameter you can play around with. The number of visible nodes is 2 times the dimension. And you see that this A here is now initialized to a small value. And I use the normal distribution. I same do with B. I do the same with the weights. And you can see now that here I need the number of particles and the dimensions. Here I simply have the number of hidden. And then I set up the derivatives. I perform iterations. I have an eta, the learning rate, which I put to 10 to the minus 3. This becomes a parameter. You can make this more refined. You can use methods like Adams, root mean square propagation. You can use with momentum and so on. And basically here, this is just a brute force implementation of a gradient descent with a learning rate, as we discussed in the previous codes. And if I run this, so let's hope this runs through here, you're going to see now that it's going to hit. So this is every iteration where I train the parameters. And I do 50 iterations. So I'm almost spot on because I have a trial wave function, which is pretty close to the final result. You see, this is pretty straightforward to implement. So it shouldn't be very intimidating to set up. But the problem now is if I want to set up the interaction here, and now you will see that it's not going to be that stable because I don't have a part in the wave function ansatz which cancels the divergence in the Coulomb interaction when the two particles are getting close. So if I rerun this one now, the exact answer, you can calculate it analytically, is 3. But you see, now it oscillates much more. You would need to tune this result as a function of the learning rate. You can add more parameters, but you see I'm getting something like 3.2428. This still oscillates, which means that I would need to think of changing the learning rate, improve the max iterations. The gradients are not going to be close to 0. And this is very much what we saw previously when we added interaction. But when I have, due to the Gaussian binary, I have a wave function which is essentially harmonic oscillator times some crap. And then I'm almost spot on. But then, since I don't have the proper Jastrow factor correlation part, my result here will start oscillating around 3.2 something. And the exact answer is actually 3.0. So one of the things which I wanted to discuss a little bit more after the break is how we can include more fermions if we want to do that. So this is, I leave this as optional. Alternatively, you can take project 1 and don't do the Boltzmann machine, but just look at the system of fermions. But I see that we don't have that much time left here. So my suggestion is that we simply look at this after the break. And that will be the last lecture which we have. And then we focus essentially on project work every Friday.